Hi guys, we are Group 2 and we conduct this experiment, dimensional analysis, and in this video we'll talk about more detail about the experiment.
In this experiment, we are trying to estimate the power requirement by scaling up from a smaller, geometrically similar model using dimensional analysis principles. This can help the chemical engineers to design systems with the help of dimensional analysis. By ensuring the dimensionless quantities such as power and Reynolds number are aligned between the model and full-scale systems. The objectives of this experiment are to learn how to scale up a mixing system from the data which we have obtained in a small-scale laboratory. This also helps to make it more cost-effective and reduce wastage of material. The aim of this experiment is to examine the impact of mixing speed on torque value. Dimensional analysis serves several key purposes. First, it minimizes the number of variables by grouping related quantities into dimensionless parameters. Second, it helps in scaling up systems, such as moving from a lab scale model to a full scale process while maintaining geometric similarity. Finally, it simplifies complex problems by identifying the most critical parameters. A dimensionless quantity is a measurement without physical dimensions or units.
Here is the apparatus used in our experiment. The diameter and height of the tank, the thickness of the baffles, and the liquid level in the 100% glycerol glass tank are measured using a meter ruler, and the values are recorded. The 0.075 meter diameter impeller is attached to the speed motor in the setup and secured with the Allen key. The liquid in the 100% glycerol glass tank is measured using a meter ruler, and the measurement is recorded. The distance between the base of the tank and the impeller, as well as the length of the impeller, is measured and recorded, following the same procedure. The temperature of the liquid is measured using the thermometer, ensuring the reading is accurate by taking it at a suitable point where the bulb does not touch the tank walls, and the value is recorded. The density of the 100% glycerol liquid in the tank is measured using the hydrometer, waiting for it to stabilize before taking and recording the reading. The power switch for the setup is switched on, ensuring that the speed motor and the torque transducers are on and functioning properly. The speed of the impeller is set to a value above 300 rpm, and the torque value displayed is recorded once stabilized. The speed is incremented by 50 to 100 rpm, up to a maximum value of 650 rpm, and the torque measurements are repeated and recorded for each speed. The experiment is repeated using the larger 0.1 meter diameter impeller, and the torque values are recorded by varying the speed of the impeller. Once the experiment is complete, the system is powered off and the impeller is detached using an Allen key. The glass tanks are switched and secured, and the experiments are repeated with the 50% glycerol tank. Once all the experiments are complete, all the equipment is cleaned in the sink.
Our results, our calculations in this experiment were conducted on viscosity and dimensionless numbers, where viscosity shows a fluid's resistance to flow due to internal friction, whilst dimensionless numbers defines a system as a ratio relating two physical quantities to a scalable system. So Reynolds number and power number are the dimensionless groups used in this instance, where Reynolds number shows a ratio of the inertial to viscous forces, which is used to determine its flow type of either laminar or turbulent, and power number shows a ratio of resistance to inertial forces. To outline a very brief procedure of how calculations were conducted would be that we would first determine the fluid properties by finding the density and viscosity of 50 and 100% glycerol using linear interpolation. We would then convert the impeller speed from rotations per minute to rotations per second to be used for Reynolds and power number calculations. Next, we'll calculate the power requirement utilizing angular velocity and torque, and then we'll calculate the Reynolds and power number for each impeller and tank configuration and plot a graph for this. Lastly, we'd calculate the Reynolds number for a 50% sodium hydroxide solution at various temperatures, densities, and viscosities. The following graph shows a relationship of the two dimensionless groups. The power number decreases inversely proportional to the Reynolds number, and we can observe a more consistent linear relationship using the bigger 0.1 meter impeller as opposed to the exponential relationship for the smaller impeller.
Based on the calculations, the most appropriate model to scale up is the 50% glycerol solution with an impeller diameter of 0.1 meters. The power required for the full-scale system can be determined using the graph on the previous slide from the power number. However, it's important to note that there are a few potential sources of error that could affect the accuracy and reliability of this experiment. These include impurities in the solution, percentage uncertainties in the measurement, and fluctuations in the rotational speed. In conclusion, dimensionless numbers like the Reynolds and the power number obtained from lab-scale experiments play a key role in designing scale-up processes. Thank you for listening.